Welcome to AP Chemistry. In this video, we will make our way through all of the remaining skills associated with drawing Lewis structures. Orbital hybridization theory is the concept of mixing atomic orbitals to form new hybrid orbitals with different energies and shapes, etc. And these will be used to form chemical bonds. It is a way in which we make sense of what we observe nature to do. So let us begin with a specific example. Although the rotating image at the top of CO2 applies here, let us use an even simpler system, that of beryllium dichloride, shown at the bottom. Beryllium's valence electron configuration is provided. Note how both of its two valence electrons occupy the same 2s orbital. This is a problem, as this atom is going to form two covalent bonds of equal energy with two chlorine atoms. It simply cannot occur in this ground state. What is required is that one of beryllium's electrons become excited, such that its new electron configuration would be 1s2, 2s1, and 2p1. Yet this first move is insufficient by itself. For if beryllium were to proceed with bonding from this excited state, it would result in two covalent bonds of unequal energy. Therefore, nature completes a second move. That is, we observe a hybridization of the 2s and the 2p orbitals, such that we no longer have two orbitals, one of pure s character and one of pure p character, but rather we now have two orbitals, both with 1/2 s character and 1/2 p character. That is, we have two sp orbitals. Note then what occurs in the case of boron trifluoride. Here we observe a hybridization of 1s and 2p orbitals, such that we now have three hybrid orbitals, each with a 1/3 s and 2/3 p character. That is, three of sp2 hybridized orbitals. In the case of methane, carbon's valence electrons occupy four hybrid orbitals of 1/4 s and 3/4 p character, or four of sp3 orbitals. In the case of phosphorus pentafluoride, phosphorus's valence electrons occupy five hybridized orbitals of 1/5 s, 3/5 p, and 1/5 d character, or five sp3d hybridized orbitals. Finally, in the case of sulfur hexafluoride, sulfur's valence electrons occupy six hybridized orbitals of 1/6 s, 3/6 p, and 2/6 d character, or six sp3d2 hybridized orbitals. Although there are a few other possible hybridizations, the compounds that exemplify these are so few in number that to cover these would be extremely impractical. Therefore, we will stop here. Now, with these hybridizations in mind, we should immediately make the connection to valence shell electron pair repulsion theory, or VSEPR theory. All VSEPR refers to is that these hybridized orbitals, in relation to one another, will repel each other as much as possible, such that a stable geometry of electron domains will result. Although this may seem like a lot of information, once you understand the context, this becomes distinctly logical. sp hybridization will always result in an electron geometry of linear or 180-degree bond angles. sp2 will always result in electron geometry of trigonal planar or 120-degree bond angles. sp3 will always result in electron geometry of tetrahedral or 109.5-degree bond angles, and so on. The electron geometry is distinctly different from the molecular geometry. That is, when bonding pairs are substituted with unshared pairs in that domain. But it is the electron geometry that is absolutely more important to remember. However, you should not simply rote memorize these. It is much more convenient to understand and commit them to memory while making sense of them. In the next set of slides, you should take a moment to get an intuitive feel for each example, as well as their names. For SP, there is only one molecular geometry, and linear is self-evident. For SP2, the root structure is trigonal planar, and trigonal is Latin for literally triangle, while planar refers to the object being in the same plane. Therefore, trigonal planar literally means a same plane triangle. V-shaped, again, is self-evident. For sp3, we have our root structure tetrahedron. Tetra means four, and hedron means head or face, literally four faces. However, do not think that the points extending from the center are the faces. Rather, think of a set of three auxiliary points coming from the center as forming the surface of one face. This is how the four faces are meant to be taken. Next, trigonal pyramidal literally means triangular pyramid, and V-shape occurs again with a different hybridization and different bond angles. Finally, you should note that bond angles will differ when an unshared pair is substituted for a binding pair. This is because a binding pair is supposed to be attracted to two different nuclei, and therefore pulled a distance away from our central atom. But an unshared pair is entirely located on that central atom, and thus exerts a greater than expected electron-electron repulsions on the other orbitals. Therefore, the bonding orbitals are pushed closer together, and their bond angles are less than expected. Continuing on, trigonal bipyramidal is literally a triangular two-pyramid shape in which both pyramids are joined together at their base. Seesaw resembles a seesaw. T-shaped is T-shaped. And linear occurs yet again through a different hybridization. You might wonder why T-shaped is not a kind of trigonal planar-like shape. But this is again due to the unshared pairs exerting more repulsions on the central atom. However, in the case of the linear shape, the electron pairs are equidistant from each other, and thus result in the linear shape. For sp3d2 hybridization, octahedral, again, means 8 faces. Again, one should not count the auxiliary points. That would only be 6. Rather, one should look at all the possible three-cornered sides. Square pyramidal is literally a square pyramid, and square planar, a square in the same plane. Again, square planar is the only other molecular geometry, along with the sp3d linear shape, in which the angles are exact due to their equidistant repulsions. Thus, we have on these slides both the hybridizations geometries, and bond angles you are required to know. You should absolutely practice using these on the structures that you have already been working with. We will now continue on to the subject of sigma and pi bonding. Now, sigma bonds are the simplest, localized, covalent bonding that can occur. The first bond in every single, double, or triple bond is a sigma bond. Along with unshared pairs, sigma bonds always reside in hybridized orbitals. However, if we are to form a possible second or third localized covalent bond, we cannot use the same orbitals. They are already occupied. Nor can we use the same location. They would repel. So there needs to be another way to form a bond without using the same, let's call it X axis. Well, we already have the solution. Other bonds can be formed around that central axis, like say in the y-axial or z-axial plane. The orbitals for those would overlap in this indirect way that we call a pi bond. It is important to note that pi bonds are formed from unhybridized orbitals that are remaining, always either of other p or d orbitals. This is important in that pi bonding does not change the hybridization or electron geometry. In order to compare how sigma and pi bonds affect chemical properties, let us take the example of ethane, a purely sigma bonded molecule. Because there are no pi bonds in this molecule, the orbitals can freely rotate around each other, and they constantly do. However, notice how the situation radically changes with pi bonding. Pi bonding keeps the orbitals in place because the pi bonding occurs above and below the central sigma bond. The only way for this molecule, ethene, to rotate is for that pi bond to actually become broken and then to become reformed again, a process which would obviously require an absorption of energy, i.e., heating. Ethine is in an even more restricted situation with triple bonding. Here, one can see the central sigma bond surrounded by pi bonds above and below both on the y and on the z axial plane. Many unique and interesting properties result from pi bonding. Diamond is an allotrope of pure carbon that cannot conduct electricity. However, graphite, another allotrope of pure carbon, which is commonly found in pencils, can. This is purely due to its pi bonding. A molecule that is essentially a small section of graphene surrounded by hydrogen is the compound benzene, shown here. The pi bonding that occurs exists in a state of resonance, which allows for the possible conductive properties that are found in graphene. We will now finally end this video on the topic of polarity after the next set of slides. Here we return to the topic of electronegativity. Electronegativity is intimately connected with our understanding of intramolecular bonding. Intra here means inside our molecule. We have three types of intra-bonding in chemistry: localized covalent bonding, which we have been discussing primarily in this unit and occurs mainly in nonmetals; delocalized covalent bonding, which we have not discussed yet and occurs mainly in metals; and ionic bonding, which occurs typically between a metal cation and a non-metal anion. The properties of both covalent bonding and ionic bonding can be conveniently described using differences of electronegativity between the bonding atoms. Note the small simple chart to the right. A difference of less than 0.4 would result in a nonpolar covalent bond. A difference of greater than 0.4 but about less than 1.7 would generally be considered to be a polar covalent bond, and a difference above that is typically considered to be ionic. Again, this is a generalization, due to the fact that we are dealing with not a fixed and definitive rule, but rather a tool that helps us to explain a large spectrum of properties that we observe. It should be rather convenient, however, to draw a simple dipole moment over each bond of your Lewis structures in the direction of the more electronegative atom. A dipole moment is a small arrow that begins with a plus sign and ends with the arrow. The plus sign showing the more electropositive end of the bond, and the arrow end the more electronegative end. In the case of F2, the bond is completely nonpolar, and there is no dipole moment at all. However, in the case of BRF, the dipole moment is in the direction of fluorine. In the case of carbon dioxide, there are two dipole moments, each pulling from the central carbon in the direction of the auxiliary oxygen atoms. Now, here we can invoke the concept of not simply bond polarity, but also possible molecular polarity. That is, not only can bonds be polar, but this can affect the overall polarity in the molecule as well. However, in the case of carbon dioxide, the dipole moments are pulling equal and oppositely from each other. Thus, they cancel each other's pulls out, and there is no overall dipole moment on the molecule, even though there are two individual dipole moments in each of those bonds. In the case of sulfur dioxide, however, each bond is polar in the direction of each oxygen atom, and since the molecule is V-shaped, there is also an overall dipole moment in the molecule in the direction of the oxygen end. Here we see some of the most polar molecules that you will encounter in our course: HF, H2O, and NH3. Finally, with a significantly higher difference of electronegativity, the phenomenon of ionic bonding begins to arise, in which an ion takes a point in a lattice conformation, attracting other oppositely charged ions in a three-dimensional array.